Ow! Hello everyone, it's November the 4th. I just watched a video where a baseball is shot at supersonic speed at a gallon of mayo. My god, that was beautiful. Alright, let's go ahead into what we have today. Sum of left leaves. What do you mean by left leaves? A binary tree and all the left side? See if I've done this before. Yes, I've done this before back in August. Given a root, return the sum of all left leaves. So left leaves, 2 left leaves in binary tree, 9 and 15 respectively. Okay. How do I know if it's a left leaf? That's a good question. How do I know it's a left leaf? Well, I mean, if I come to the leaf, basically I just need to pass another one, right? Either left or right. So if I am a leaf, if it's a none, that's going to turn 0. If I'm a leaf, like if I don't have, I return, no, we'll always check. Right? If I am a leaf and then the root, we have at least 1. So if I am a, oh, hold on, look at this. This one returns 0. So that is not a left leaf, right? So by itself, the root by itself is not a left leaf. So when we pass in, we pass in a right, okay? So in the pass, whether you are a left or a right branch, right? So we can say 1 or 0. 1 or 0. If we pass a left, we set to 1. If we pass a right, we set to 0. And that shall work. And then if I'm a leaf, I'm just return. Okay, I think I have this. I have a scheme for this. Let's see if we can do this without having the error, because I checked last year, August. Are they just redo everything from last year? It feels like it, right? They're just like, okay, we're just gonna do the same questions last year and nobody will notice, because nobody will keep doing this since last year. Well, I am, and I know. Either they're being lazy. Actually, I don't think they're being lazy. They just don't want to automatically show all their questions. Maybe. All right, so we can do the same trick. All right, we can say is left, and that's going to be an int, and it's going to be a 0. All right. So here we're going to do, we say if not root, that's going to return 0 no matter what. All right. And otherwise, if not root dot left and not root dot right, I'm a leaf. I'm gonna return root dot val times is left. All right. Otherwise, then I'm gonna just do return sum of leaf root dot left passing 1 plus sum and root dot right 0. Okay, let's give this a shot. I think we have a couple of test cases. Oh, I have 2. Doesn't matter. Try these 2. Not defined because it has to be self. Self. Again. Awesome. All right. Do we dare? Yeah, let's go. Yep. All right. I'm too lazy to write the other version. Let's just end with this. So this is DFS. All right, DFS and ON with 32, so 80%. And technically, we shouldn't change the requirement, but it doesn't really matter, honestly. That was from a year and a half ago, a year and 2 months ago. Leaf. Oh yeah, that's the same thing. And then return s. No root. Oh, I like this version, right? I like this version. This will just use a 0 and a 1, and then everything can be simplified to the same thing. Yep. Okay. So we're done for today. Let's roll another one. I'll do the same thing. I'm gonna roll a medium. Yeah, they just don't allow me to say open a new tab. That would be cool if I can open a new tab. I'll speed thing up. Insert, delete, get random. Oh, wait, I done this just a month ago. Same probability. Ah, I think I remember. It's an array, right? And every time we delete, we will find the value, swap it to the end, and then pop that. And this one makes sure that we can keep everything inside the array. All of them are valid. Yeah, I remember this. And it has to be a set, right? So everything has to be unique. Yeah, I remember this. But now I'm gonna do it again because I've done it before. So roll again. Yeah, I feel like, I don't know, what's the likelihood that I kept rolling into the question I have done before? IP to CIDR, IP to CIDR. Oh, that's the IP address thing. Nah, this is frustrating. Go through this and then I have 22 pages. We'll just pick the first one that we haven't done, right? So how about this? Best time to buy and sell stock. Have we done this? I have not done this? That was surprising. I haven't done this. All right, let's do this. We're given an integer array. Is the price of a given stock. On each day, you may decide to buy and sell stock. You can only hold at most one share of the stock at a time. However, you can buy it, then immediately sell it on the same day. We can buy it and immediately sell it on the same day. Huh. So buy on day 2 and sell on day 3. And buy on day 4. Wait, 1, 2, 3, 4. Wait, hold on. Buy on day 2, sell on day 5. And buy on day 4 and sell on day 5. Buy on day 1, sell on day 5. Wait, what's the restriction on this one? Is the price of a given stock on the ith day. Yeah, buy or sell. So there's no holding. So just buy and sell. And you can hold at most one share of the stock at any time. However, you can buy it and then immediately sell it on the same. Why would I buy it and sell it on the same day? Yeah, why would I buy it and sell it on the same day? If I buy it and I sell it on the same day, the price doesn't change. That feels weird. So isn't this just a buy and sell? What's the difference between this and the previous one? I mean, basically has, if we go back to the state machine, right? So I have two states. We have buy, and it's a holding state, and empty state. From empty to holding, we're gonna buy. From holding to empty, we're gonna sell. And we can choose not to, so everything can go back to themselves. So there's no option, right? So we have the starting holding and the starting empty, and for the holding state, it just start with the price, right? I think that's what it is. So empty state start with 0. A holding state, the profit that we cannot hold, and so I think holding state, remember, starts minus infinity, right? And each state and each time, so a new holding will be the maximum of holding. We don't hold anything, or we can sell. So minus P, minus price, and then the empty state will be the same, max empty, because we can do no option, or we can sell, which is plus P. So H plus P, right? Yeah, I feel like, hold on, let me just write it here. So we have a holding state and an empty state. And like I usually do, holding state are set to this, empty state is 0. And then for P in prices, right? And say HE equals to, well, the new holding state would be the maximum of the previous holding state, right? Which just means no option. Or holding state is empty going to, so the empty minus P would buy. And then the empty state will be maximum empty state for the previous holding state with plus P. And eventually we're gonna return empty state. I don't know. That's sufficient for this? Yeah, I guess it is. Yeah, I guess it is. So this is just, I mean, this marks the end of all the stock markets thing, holding stocks. It's surprising that I didn't do this before. So 122, right? So 122. Yeah, we still need to follow the routine, right? We still need to do this, just keep a record. So yeah, I don't see any tricks in this. So it's this basic state machine with no obvious trick, right? And then running ON, and we run it pretty fast. This one, 56, 93, 3% right? And I don't have to do this. I'm just gonna glance at the solution. All possible sets of transactions. Peak valley approach. Peak valley approach. Simple one pass. So looking for every peak following a valley. Simply go on crawling over the slope and then keep on adding the profit obtained from every consecutive transaction. In the end, using the peaks and valleys effectively, but we need not track the costs corresponding to the peaks value alone. We can directly keep on adding the difference between the consecutive numbers of the array. If the second number is larger than the first one, and then the total sum we obtain will be the maximum profit. Okay? So we consider that the sum of A, B, and C equal to the difference D corresponding to the difference between the heights of the consecutive peak and valley. 1, 7, 2, 3, 6, 7. So as we go through, if price I is larger than the previous one, the max profit, we're going to add it. So it's just these two difference, right? And if this one is larger than the previous one, so if the next value is higher than the previous value, then we can add that, because if I have the next one, then that can definitely be compared to the previous one. Now this is the direct result of we don't have to, there's no holding state, right? So we can buy and sell anytime, at any time. Therefore, the profit we gain on any interval, right? On any interval can be combined. Yeah, that's the thing. Anything can be combined. But what if I have something like here, right? And then I have something here. What would that do? That, I don't know about this. I mean, this is a strange example. Yeah, what, like here, is I adding this one and adding this one? What, is that right? I mean, and are we ignoring this one? 7 and 8. Hold on. Let's start from 1. If price I is larger than this, like we record this, and we record this, right? And record this, and this we don't record. But this, isn't this one also recorded? False equal true. Wait a second. I don't understand. Let me use this. I think I'm a little bit confused. How is the last profit is not counted? Huh. Let's print I, prices I, prices, actually I minus 1, prices I, and profit. So I start from I, prices is 1, 7. The profit is 6. Wait, how is the profit 6 to begin with? Oh, because it's 7. It's 6. Okay, we start with 6. And then we stay at 6. And then we have 7, which is adding this. Hold on, 1, 7, 2, 3. This is a 1. This is a 3. Now we added a 10. Oh, we do add every single one. Oh, I see. What was I thinking? Yeah, what was I thinking? Yeah, that's true. So every jump, we calculate every jump, right? Because if it's a consecutive jump, we can always break it down to individual jumps. So all we need is compute individual jumps. And since there's no limit on how many times you can buy and sell, we just buy and sell as many times as you can. It makes sense. It makes sense. Okay. Now we don't need to. But what's the difference between this and the others? The others have. You can only buy once and sell once. Well, if you buy once, sell once, that's also simple. That's just you buy the lowest, sell the highest. Or you can search from the highest and search from. No, I think that's also. That is also. Oh yes, that's also. I remember what that one does is, the holding state will always be minus p because you only can buy once and sell once. You always minus p and then that. All right. Now we're gonna go back to. Let's upload this. All right. Let's pull up all the others. The cooldown with the transaction fees. Yeah, every time we hit this, it basically just go through every one of them to refresh the memory. What is this? Like maybe this only can buy once or twice. So I think when that happens, it's just the first time when you buy, it's different. At most 2 transactions, right? So at most 2 transactions. This is the latest attempt. To say at most 2 transactions, we have 2. And if you take a look, that is the trick. The first one, right? The first one we can stay, because stay is no option and no operation, so we can always stay. But because we have a limit on how many you can do, so the first one is always minus p. It's not like e minus p. It's always this. And then there's the first sell, second buy, second sell. Yep, that makes sense. This is yeah, I think that's the one. This is at most k transactions, right? At most k transactions. Well, when you do a most k transactions, you simply just have an array for all this and all ESs, right? So this is a k transaction, and we don't have to worry about the first one. We don't have to worry about the first one. Why we don't have to worry about the first one? Because the first one as the holding state will be the previous current holding state or previous empty state minus p. Previous empty state, the previous holding state. Plus p, but not previous. As it is previous, right? Previous holding state plus p. But the key, right? The key is the holding state. Because the first holding state, and we start from 1, right? We start from 1. So 1, the first holding state. And we will do itself or ES, that's a 0. Oh, we do k plus 1. We do k plus 1. So everything starts with 0 and everything starts with this. So we have say for 1, the case of the first transaction, it's going to be, because it has to be minus p. but this is a 0, so 0 minus p. And then this, I see, okay. That's that. Okay, what's this one? With a cooldown, right? With a cooldown. With a cooldown, we just add another state, a cooldown state, and another state, right? So I have a holding, empty, and a cooldown state. And then next holding state is holding state and E minus P. And then next empty state is E, or because a cooldown goes there. Next cooldown is this, and yeah, that's fine. The last one with the transaction fee. Each transaction takes max profit is achieved. Is this the same way with a transaction fee? State machine. Yes, I think just every time you also minus 2. I think every time is minus 2 because you have to do the transaction. Exactly. That's empty holding. And the whole empty state will be, because that's the transaction we buy, so we need to minus the fee. And then this, yeah, that's, and then we return the empty state. Yeah, so all of them are the same. In terms of the basic idea of state machine. And state machine is just another way of describing dynamic programming, but the description is much better, much easier to reason with compared to if you want to set this up on dynamic programming. Okay, so that's that. We actually can roll another one today. Okay, so next one will be Lru Cash. Oh, this might not be easy. Let's see if we can handle this in half an hour. All right. Oh, look at this. People are loving this. Nope. Yeah, of course I haven't done this before. A data structure that follows a constraint of a least recently used cache. Implemented. This is Wikipedia. Yeah, it's going to be Wikipedia. Initialize the Lru cache with positive size. Okay, what size? Get the value of the key if the key exists, otherwise return -1. Put key value, update the value of the key if the key exists, otherwise add the key value pair to the cache. If the number of keys exceeds the capacity from this operation, evict the least recently used key. The least recently used key. Okay, so put size is 2, put 1 1, put 2 2, get 1, put 3 3. Lru key was 2. Leastly recently used, because recently used is 1, because I get 1. What if what happens when if I don't use it? I just put 1 1 and 2 2, and I want to put 3 3. Who gets evicted? The least recently used key. Well, if that's the case, I'm pretty sure it's going to evict. Because you put 2 2, so 2 2 considered least recently used. So it'll be 1 1. Get 1, get 2, not found, put 4. Least recently used key was 1. Hold on, why least used key is 1? So recently used is 3, right? Because currently it's 1 and 3. Because I put 3. But that's the recently used. So least recently used key was 1. Evicts 1, caches 4, 3. Hey, I want to confirm. So it's fine. I'm just return the same value. I want to return. That should be fine. Okay, I want to go to put. I want 3 put. I want to see which one gets put inside. Okay, so put. Awesome. So nothing's going to get printed out, right? Put. Let's see. If I run it, what's going to happen? Indent block. I cannot do this. Self dot full. I'll just pass. Oh no. Oh! Oh, the get will get will be wrong. Okay. So I need to call get, right? Put. Then we need to get. Yes. I want to peek inside, right? So we need to get. Get which key? Let's get, I think 1 is the leastly used, right? I think 1 is leastly used, so I should get 1, should give me -1. Yes, 1 is leastly recent used, because the recent used is 2. I see. Capacity, key value, and the key value are all integers. Yeah, okay. So we just need to keep a record of which one is the least recently used. What will be a good record? I mean, the key value pair is going to be a dictionary, that's for sure. We just need to have a mechanism to keep track of the least recently used. So every time a new key gets mentioned, right? Every time a new key gets mentioned, there gotta be some weight, right? There gotta be some weight inside the key. So priority queue will be something we can use, but then we have the same issue because the key kept updating, right? The key kept updating. What is the mechanism? This is the same problem I had the other day. Oh, I totally forgot. How did I solve it? It's constantly changing. I think I solved it by not thinking about it, but I think I have to think about it today. Because all the keys are integers. We need to find the least commonly used, the least recently used. That's a good data structure. So a key comes in. I need to update. And update the key. Alright, need to update the key. And we need to find the smallest. Oh yeah, remember in that question I just go through the entire thing and then look for the smallest. That doesn't feel right in this one. Because that will be like O(n) squared. But a priority queue I have to create. Yeah, priority queue is also, it's convoluted. I don't think it's a priority queue. Gotta be a very smart way to do this. Yeah, so I have key and value, right? So I have 1 on 1, and I record the recently. I know the recently used is 1. And then 2. I know the recently used is 2. So 1 becomes the recently used, right? And then something else comes in. Isn't that just a queue? What if we put into a queue, right? 1 comes in, and then 2 comes in, right? So we keep appending to the end. So that's the queue of the keys that has been called. And every time we do that, we have a list is on the front, right? Not exactly. So if another key, if the key is the same, so like we get 1, right? So when we get, so we put 1, we put 2, so in this stretch is 1 and 2, and 1 comes again, and we're supposed to put 1 into the queue. But now we'll also check if 1 is the same as the least used, so we just pop the least used. So every time we add a new one, we have to check to the front, and then pop left of if we have consecutive the current key. We just keep popping, keep popping, keep popping. But what if I call 1 multiple times? Right, we call 1, and I call something, and I call 1 again, and then we call 1. If we keep popping, and this 1 will be at the front as well. That's not the leastly used, because we might have something else that's recently used is 1. So all the 1 records shall be eliminated. All the 1 record shall be eliminated. So yeah, we used key 1. So 1 record gets eliminated. Swap. What about swap? Like if I know the index, so I know the index of this, right? And this is in an order, at least the used order. So when I do that, I say this needs to be swapped with something that we cannot swap with the end, because if we swap with the end, and we can pop it, but the one swap forward, that one is still the least recently used, so we have to swap back. That's not the case. Most recently used. Right, we have 1, we have a 2, and a 1 come again. How do I know that 1 is the recent used and 2 is the least recently used? 2 gets mentioned the last. I mean, priority queue definitely works. I might just give that a shot, even though I don't like it. I don't like how it's just too convoluted. Basically, when I create a priority queue, right, and then the element of priority queue are objects, right, and then that objects hold a value, which is the number of times that this key has been mentioned. So the least recently used will be the one, like we have a time tick, right? We have a time tick, and then every time it's used, the time tick will change value. The time tick always go up, right? Always go up. Now, every time, if we call get, we call put, we have a tick, so we'll keep ticking up, and we'll change the value. So every time we can use the priority queue to, so it's like login time, right? We do login time to bubble up the ones that has the earliest tick. So that was the one that we need to remove. Okay, I can try that, but I just, again, I feel like this is just unnecessarily convoluted. Right? Unnecessarily convoluted. I feel there should be an easier way to handle this. Yeah, like that's the tick, right? I'm using the tick idea. So I have two ways of thinking. One is we have a type of order, right? We have a type of order that gets pushed in with regards to when a key is mentioned, right? The current key mentioned always pushed to the end of the array, So we know closer to the right side, those are recently used. Close to the left side are old. That works, but it has a complication. That is, if the same key that has been used before, like very early on, and I mentioned it right now, right? Like will be a situation like this, right? We have, say, the key 1 I mentioned, right? So looking here, 1 I mentioned, and I mentioned 2, and I mentioned 1 again, and I mentioned 2, 3, 4, 5, right? Doesn't matter. And then I mentioned 1 again. All right, so when I mention 1, but actually in this case, if I mention 1, I shall see that 1 has already been mentioned, so I shall remove it. Okay. So if a value has never been mentioned before, right? If a value has never been mentioned before, what if I mention 1 here? That's the thing. Yes, yes. So I mentioned 2, right? I mentioned 1, I mentioned 3, 4, and then I mentioned 1, right? Then what do we do about this 1? What do we do about this 1? I don't know. I mean, what do? We don't do anything. Like until we mention, I mean, if I pop, like it could be get, right? I get 1, and then if I want to push in 5 and I need to pop something, then I can look at this, right? So I can pop 2, which is fine because 2 has never been mentioned again. So I can pop this, right? And then add a 5. But now 1 is not the least recently mentioned. The least recently mentioned is 3. How do I also pop 1? And we have duplicates. Okay, we have duplicates. So if we have a set with keys that has been mentioned duplicate times, right? We mentioned duplicate times. What does it mean by mentioned duplicate times? It means when the key is mentioned again, it's not at the front of the list. So we need to mark it, which means the front of the list is not true. That's not the true usage. So we need to pop it, right? We need to pop it. So we can count how many times 1 is mentioned. How many times 1 is mentioned. Each key, we count how many times each key is mentioned. And then, if the count is 1 and you are at the front, you are the least recently mentioned. If the key is more than 1 and you are at the front, then you are not the least recently mentioned. So we simply should pop you and keep looking for the next one. Right? So in this case, right, that's fine. So we have 4 keys. Now say we want to add 6. Right? And we cannot add 6 because we reached the capacity. So we're going to pop out. So we look at the front as 1. And then we go into the counter and say 1 has 2 counts. That means this is not the least recently mentioned 1. So we need to pop 1, but not, and then reduce 1 count, but not really remove 1. And I'll keep looking at that 3. It's like, okay, 3, you have a count 1, and you shall be removed. So 3 gets removed, and then 6 get put in. That's my work. Okay, let's try this. Yeah, seriously, this might work. If this works, this is the data structure to handle all of those problems. I mean, I've been having these problems for so long. Well, if I remember, that is prerequisite to, remember. I tend not to have a good memory. I learn fast and I forget equally fast. That's my curse. Learn fast and forget fast. How about that? All right, we don't have to do this, so it's not full. So this is going to be a counter. Right? We have a counter. Let's just do a counter, which I like. So from collections, import a counter. So we have a counter. And then we have also self dot. What is this? This is the cache. This is the cache. Cache is just going to be a dictionary. Nothing fancy. So when we get, right? When we get, we also need self dot least recently used. What this? No, it's going to be a deck. So I'm going to do a deck. Right? So it's going to be a deck. So get. Right? What do we do when we do get? So we simply say return the value, otherwise return -1. So we can always just return self.cache.get key -1. But before that, we need to say self.counter, right? Key plus equal 1. Increment a counter. And self.ru.append key, because this key gets mentioned, right? Now here, we're going to put, right? Oh, and it also needs capacity. Self.cap equals capacity. So we say if len self.cache is smaller than self.cap, then we simply just add it in, right? We simply just say self.cache key equals value. Easy peasy. What do I return? Update the value if the key exists. Otherwise, add to the cache. Exceeds when evict, but we don't return anything. So we do that if it's smaller. Well, we always need to do that, right? So we always need to do that. After we do it, then we check, right? So we'll always do that, and we do this as well, right? We do this as well. Hold on. Should we counter plus equal 1? We always do this, right? And after we do this, if the size is larger than capacity, that's when we know we need to remove something. Who do we remove? Well, if I already increment the counter, so this current key is safe, right? The current key is safe because I have the counter already. So again, these two will always happen, and then we do this, all right? And then we're going to see if len self.cache is, if it's larger than capacity, right? That means we need to purge one of the things. How do we purge? We're going to look for, we're going to say while, right? What do I say? So look at the front. Look at the front of LRU, right? The front value, if the front value is if the front value has a counter is 1, then that is the least recently used. Otherwise, we're going to pop it. All right, so we're going to say while self.ru and self.lru 0. right? And then it's going to be self.counter. This is larger than 1. It's more than 1. Then self.lru.pop left. Right? We can just pop left. If the front, well, then this the key equals this. It can even be fancier. Self.counter. Right? Minus equal 1. Right? So which means the front of the LRU array, if the front have mentioned more than once, then that is not the least recent mention. So I pop that and also decrement the number of mention. And then I come back again, right? And I say, oh, it's another key that has been mentioned before, as mentioned more than once. I do it again until, after we pop, we do it again until we see LRU 0, right? LRU 0 is actually LRU will definitely not be empty because len is larger than self.cap, right? So it will happen that this will become 1, right? The front is 1. Now if the front is 1, so the next thing is the one that we need to delete. So we simply call del. So we call key least recent used key equals self.lru.pop left. So when pop left, this is the one we're going to remove. How to remove? A couple of things. First of all, counter LRU key minus equal 1. So we popped, we do this, and then this key needs to say del self.cache LRU key. And that's that. Okay, let's try this. Yeah, that's a good test case. Use example. Let's put 2. Actually, the example should be good enough. Huh? Is it this? Yeah, I think we got it. Try it. Uh-oh. Uh-oh. Got it wrong. Runtime error. Oh, what happened? Wait. I don't understand. What's the error? Key error. We have a key error. Huh? Hold on. Why would there be key error? A key error. Which means there's no key, right? So key error 12. Where is 12? We try to pop 12. Well, we did put 12 in. Then 12 was never mentioned. Why would there be a key error? Alright, I hate to do this, but we have to debug this way, unfortunately. I have no idea. Okay, so what do? We need to, what's the capacity? Holy shoot, capacity is 10, okay? So what do? We check the LRU, right? We check LRU, and if it's this, yeah, let's just print self dot self dot, let's say counter, self dot cache, self dot LRU. I don't know. I'm probably key as well. Okay, so, oh, geez, this is not easy to read. Do I even have everything? Standard output. Deck is this. Key is 13. Now, I don't think it prints every single time, though. But if you look at the counter, is this the last? Look at the deck. It's 13 as at the front. The recent is 10 coming in, right? And then we have a counter is this. Cache is this. Oh, this is interesting. Deck has 12. The counter has 12. But here we don't have 12. What? Okay, we have 12. 12. Counter 12. 12. 12 gets changed. Mm-hmm. 12 gets changed from 24 to 2. So I'd expect deck. Okay, that's interesting. Oh, because I didn't, probably a couple gets earlier. Anyway, so that 12 is here. 12 I just got. So the counter 12 is 2. Right? And the deck, I only have one 12. Oh, I have two 12s. And counter 12 becomes 1. 12 changes back to 24. Yeah, look at this. 12 here is 20. Well, 12 is 20. Hold on. 12 is 24. Oh, I got confused. This is the counter and this. Okay, you should not do it this way, man. We do need key. I need counter. I do need all three. But I think in order to debug it better, we have to print them like this. All right, print this, and I'll print one more just so that'll be easier for us to debug. There we go. Now we know. Let's see the deck. Deck I have 12. Counter I have 12. Yeah, but why? Wait, is the key error? No, I don't think it's rated 12. Really? Is this the last trace? I don't know. Counter 3 mentioned 8 times. That should be same number as here. 13. It mentioned 4 times, right? And then if I add 10, right? I want to add 10. We can add 10. Doesn't change anything. And then we call a bunch of gets. 3 now is 8 times. And deck is this. 13, because I already pushed in 13. Alright, I have no idea. Okay, let's, we know this is the key error, so we're going to try and then accept. Alright, so say accept key error. Or we're just going to print. And print RRU key as well. Let's see, what the heck is going on? LRU key is 12. And actually pass. Wait, what? Hold on. What happened, I think, is 12 is 0. And then inside the deck, 12 gets popped out. Okay? So in the deck, 12 gets popped out. Why? Because the counter larger than 1 I say LRU 0, right? If the counter is larger than 1, then the counter of that on the pop left minus equal 1. So if the next one is equal to 0, it will come out. How would 12 be 0 but still be inside? Yeah, it's pop left. So which means 12 is inside while it is becomes 0. 0 means it has not been mentioned. So the counter right? I check, right? If let's say if my cache size is larger than cap, then I remove the least recently. Look at my list and look at the first one, and then and say how many times that one has been mentioned. And say it's larger than 1 time, so 2 times, 3 times. If it's that, I say this one can be popped. Don't worry about it. So self.counter of that with minus equal to 1. Yeah. It shall. And then LRU key is equal to this. I don't understand. LRU key, right? Because when I stop is I pop left, right? And then I check this with minus equal 1. I come back, so I pop left, and then the front is larger than 1. And it's not larger than equal to 1, right? That's equal to 1. So it's equal to 1, and I do this, and I do this. That make it to 0. Then I want to delete it from the LU cache, from the cache. That is the only place I will delete it from the cache. And the cache does not have 12. Cache has 5, 1, 8, 9. Cache does not have 12. So that's the thing. I need to see. I need to see the cache. Oh, yeah. What was the issue? Yeah, we always, these two happen every single time. Right? We always add a key. We always do this. This is to get, which is fine. And this is to add, right? We add a key, which means if 12 comes in, 12 is already inside. This 12 has a 12, yeah, well, whatever, right? And then this is error. Let's say before error. Let's print something before error. Self.cache. I don't know. I have 12, 12. Oh, I removed 12 here. Twelve gets removed. So 12 is already removed. At some point, 12 is removed. Okay? At some point, 12 is removed. I have 12 here, but I don't have 12 here. So 12 is removed because 11 is pushed in. So 1224. 11:30. 11:26. So when 11:26 comes in, 12 gets removed. Okay, so let's say, and let's print self dot counter 12. All right, 1, 2, 2, 1, 0, 0. 1 again. I read 12. Oh. Oh, I read 12. It is the leastly used. Oh, but if the key is already removed, then we should not. Yeah, if the key is already removed, yeah, that's what happened. 12 is already removed. And then I try to read 12, right? 12 is used, but that shall not go inside LRU. Because LRU, the whole purpose of LRU is every key in LRU must be inside the cache. And if you have already removed, you should not be inside. Ah, made sense. Now it made sense. So basically we say if key not in self.cache, right, we return -1. Otherwise, we do this, this, and then return self.cache key. And here we can do beforehand because I'm going to add the key no matter what. The key will exist in cache. Okay, this I think will be right. Okay, this will be correct. There we go. This one is correct. All right, try one more time. There we go. Good. Yeah, so yeah, a little bit poo-poo right there. But we got it. All right, so 146. Well, we use a deck. Basically, as a queue, we use a queue to monitor the sequence, the time series of the keys used. The queue represents the potentially least used key. However, if a key has a counter larger than 1, that means this key has been used not only at the beginning, at the front of the queue, but also somewhere else in the queue. This makes the key not LRU, not least recently used. Thus, we shall pop this key and search and look for the next. The true LRU key is the one at the front of the queue and has counter value equal 1. We when the LRU key needs to be evicted, we shall use that key. So I hit a bug, right? I encountered a bug. I encountered a bug that is quite difficult for me to debug, quite difficult for me to resolve. The problem, right? The problem is that when a key is used in get call, but it is already not in the cache. If when a key is used in get call, but it is already not in the cache, we shall not record it in the queue or counter. I didn't realize that and got hit by a key error when trying to remove a key that is already not inside the cache. So I think amortize, I can say it's 01. 01 for get for sure, and a worst case, right? Worst case is the ON for put, because we have this, right? Have this. It's the worst case. Like we can do, we just call get call, right? Tons of get calls. We do a ton of get calls, and then the RU becomes so big, right? Becomes so big. And then when we want to put a new one, and I have to go through pop out everything in the RU because every one has larger than one, right? So worst case is O. Well, actually, it's not ON. Worst case is O number of get calls so far for put, where N is the number of consecutive get calls. Finish at 792 and 77. So let's check. The smart people, come on. Show me. The smart people. Hash table and doubly linked list. Yeah, I do think hash table keeps track of the key and its value in the double linked list. Oh, hold on. This is, oh my god. Oh my god. Now we talk about thread safety, which Python doesn't have. It might have very soon. That node can remove itself without other references. In addition, it takes constant time to add and remove nodes from the head or tail. We don't need to check the null node. New node to the right, and the linked is key value, okay? Remove an existing node from the linked list. Move certain node in between the head. Pop the tail. Cache linked node equals cache. So we have a cache as well. Cache is a hash table, so integer and a node. Okay. So when I add cache.get key, that's the node. It should never be this. and move the accessed node to the head. This dot move to head. What's move to head? This dot remove node, so I can remove myself. Pre equals node dot pre, post node dot post, pre dot post equals post. So it's remove. So I remove myself and add node, which is add node to the move to head. Okay, so node dot pre, add node, add the new node right after head. Oh, the head is the dummy, right? I think the head is the dummy. The head is the dummy, I think. Hold on. What is this head? Private, 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 public. Head is this. Wait. Can you access this head? Okay, I guess this head, we can access it. Yeah, I think this head, we can access it. Even though, because the head is, wait, where does this head, oh, here, private head. Okay, so yeah, it's defined. So we always, the new node right after head. So pre equals head, post equals head of post, head, node dot pre, node dot pre is head, node dot post is this. Head dot post dot pre equals node, head dot post equals, yes. So we add node, so we push this to the front. I see. We push that to the front because that means it's the recently used, right? It's recently used. So when we say get, we grab it, move it to the head, and then return its value. And I want to put, we get a key. If else, we just change it, move it to the head, okay? Otherwise, node is null, which means we don't have it. Then we're going to create a new node. And then this dot cat dot put, that's fine. And we move it to the head. And then count this. If count is this, we'll just pop tail. Doubly linked list. Every time we mention, we delete itself, put it into the head. We delete itself, we put it into the head. Right? Every time it's mentioned, we just move it to the head. And every time we need to remove, we simply just pop in the tail. That's how you move things around. Wow. This is good. Doubly linked list. It's deck, and this is my version, right? Deck. Ooh. Order dict. Yeah, well, I don't have time today, but I actually would like to implement Let's do this. I don't have time, but maybe I can still squeeze in. Right, so we need a list. We need a double linked node, right? Self, what do we need? Well, we need a key, the value, and then we have self.key equals key, and self.value equals value, right? And then self.pre, none, self.post, pre-post, yeah, none, right? And we can actually, well, the value is 1, 0, so we can default equals -1 and -1. Right, so it's a double linked list. Okay, so we have a self.head equals this, self.tail equals this, right? Head and tail. Well, do we need a tail? Maybe we don't need a tail. Yeah, this head is just a dummy, right? It's a dummy head. Maybe we don't need a tail. We do need a cache. But we don't need this. We need the capacity. And then we do need some, let's say, we need some functions to, for example, remove, right? Remove a node. Get this. I don't return anything. How do we remove a node? Well, because it's doubly linked, right? Oh, I do need a tail, so I remove. When I remove, no, I don't like it. So just remove a node, right? Remove a node. Well, we should always know tail as well. I'm gonna call it head and tail. Head, self.tail is gonna be none, right? Just no. Self.head, tail. Let me think, what would be the easier implementation? So always the tail, the front. So we always remove this one. Ooh, maybe it is easier that way, right? So we have these, and then self.head.post equals self.tail, and self.tail.pre equals self.head. So head and tail are static. So head and tail are static, right? They don't move. They just stay where they are. So when I'm going to remove a node, it's guaranteed that it has a front and has an end. So we simply just say pre equals node.pre, post equals node.post, and then pre.post equals post, and post.pre equals pre. So that's how I remove a node, right? And def move to head self node. Node can be a doubly linked list, right? So this one basically just add. I see. So def add to head. Add. Just add. Add means add to head. Right, so node, this one, add to head. So we're gonna say, how do we add to head? Well, post is going to be head, self.head dot post, right? And then we're just gonna add self.head dot post equals node, right? And then self.head.post equals this. And then node.pre equals self.head, right? And then node.post equals post. Post.pre equals node, right? So that's add. So when we say move to head, we simply call self.remove, and then remove the node, and self.add the node, right? Yeah, so we can do this. Get, say, node equals self.cache.get key, none, right? And say, if not node, then turn -1. Otherwise, we're gonna say self.move to head node and return node.value. Right, node we can move because that's one just being used. Put again. If we put, we always call self.cache key equals, right, self.cache key equals double linked list node key equals key equals key, value equals value, right? So once we do that, we add it to the cache. Now we're gonna say self.add, right? We always add it to the front. We just mentioned. So the node is going to be self.cache key. Oh, it depends if it exists. If key is in self.cache. If key is in self.cache. Nope. Do this again. Node equals this, right? No, if key not in cache. If key not in cache, then we do this. And then node equals this. So we grab the node. I don't like it. If key not in cache is going to be this. Else, if key is in cache, then self.cache key dot value equals value, update a value, right? And then I grab the node. You don't have to grab the node, we simply just Okay, if key not in cache, we add a new one. If key in cache, we change it, and we simply call self.move to head self.cache key. Right, that's it. That's all we need to do for here. Now for this, we do that, and then we need to say self.add self.cache key. We add it, right? And then we need to check. We say if oh, how do I keep track of the capacity? We need a count. So we need a capacity and we need a count. That will be 0, right? And then if not in cache, blah blah, we say count self.count plus equals 0, equal 1. And we say if self.count is larger than self.capacity. Now that's what we need to remove. Remove the last one. So we simply say self.remove node with self.tail.tree. We just remove that one, and that's it. And else we do this. None of these. Okay, let's give it a shot. Oh, of course. I also need to add this. Let's see. Incorrect. All the get call becomes -1. Get is right? We need to get the node, and if the key is not in, that will return -1. Otherwise, we do this, we return this. It's the put. So I put get is correct, and I put again, right? I put again. 3 is not in the cache. So create a cache or equal to the node, and I will add self.cache key. So we add it, the count plus equal 1. Oh, I forgot to here. So self.count minus equal 1. Try it again. That's still not correct. That's weird. Key not in cache, self.count plus equal 1, right? And then 3 comes in. Now count should be 3. I say 3 is larger than self-capacity. So I need to remove, because every time a new one comes in, I'll always add. Add is right, add it next to the head. So the last one, and I say tail.pre. Hold up. Something is not right. I did not remove it from the cache. Yep, I think that's the issue. I did not remove it from the cache, so I shall remove this and tell self.cache key. Oh wait, no. Oh, I see. I need to do this first. So this thing dot key. So remove it from it, then remove it from this. Now I shall get it. There we go. Try this. This is better. All right. So this doubly linked list solution. Good question. This is a good question. Very good question. Did I upload this? I did. Double linked. So doubly linked. I think that's what the term. Doubly linked list. Doubly linked list plus hash table solution. Courtesy of this. I remember struggling with how to find with doubly linked list, it is 01 to move any node around the linked list. And to move any node in the linked list to the head, right? Thus, when a key is mentioned, used, right? If key is mentioned or used, we simply grab the node, grab its node, and move it to the head, indicating that it has to the head. Thus, the node at the tail of the linked list is the node at the tail of the linked list is node at the tail is the least recently used key, right? So that's that. And I follow the discussion post to use dummy head and dummy tail, which drastically simplifies the logic of adding and removing nodes, because it is guaranteed that there exists a head and tail in front or behind me, behind any node. Good solution. It's a very good solution. All right, that's it. It's a good question. All right, 3 in today. Not too bad. I'll see you guys tomorrow. Adios.